So we are going to talk about then hash functions. So we'll talk about what is a hash function, why do we need a cryptographic hash, and some sample cryptographic hash functions. The hash functions probably most of you have already used in one context or the other. When you want to put something in a table, and so what you do is you take the key, hash it. What hash does it randomizes it. So not all the numbers go into one part of the table. They go uniformly in the table, right? And so basically, hash function can take any variable size input and create a fixed size output because fixed size is the size of the table. You want a number which is between 1 and the end of the table. Right? How many people have used hash out of hash before? All right, so that's what it is, right? Basically, so hash is good. Now the thing is, it should be easy to compute, and it should be pseudo-random so that it distributes over the table. Because if you just take, the last few bits of the number, then you will just end up at the very small part of the table, and you will have. Another thing with hash is there can be collision. So two numbers can hash to the same value, right? So you want a hash function that doesn't collide that often. That means it has to be random, right? All right. So for cryptography, we need the same thing. We need variable size input, fixed size output, efficient computation, and pseudo-random. Those four things come before they continue. But we also need them to be pre-image resistant. That means they have to be one-way functions, which means that given M, you can find H, but given H, you cannot find M. They are one way. Given you see in the previous slide, you are given M and you do the hash and you get the H, get the location. But if I give you the location, you cannot find the message or the key. So this is called pre-image resistant, one way. Then we want them to be second pre-image resistant, which means that they cannot collide. They're collision resistant. So you cannot find a Y such that Y will hash to the same location as X. And this is important cryptographic thing because you will see we use hashes for some secure applications. If somebody can change the number and comes out to the same hash, we will not be able to find that they changed the message. Right? So we don't want them to be easy to change the message. So basically, it's very difficult to find another Y that will hash. If this one says it is difficult to find any value M that will hash to that value, but if this says any other Y that will hash the same value. And then strong collision resistant means that even if I don't give you X or Y, you cannot find two X or Y, any X or Y that will hash to the same value. That is very, very strong condition. If you were to look in a Venn diagram, and I don't think this diagram is in the book, but could be, is that strong collision resistant are very small subset of hash functions. If something is collision resistant, obviously it is second pre-image resistant. And some of the pre-image resistant are second pre-image resistant and some of them are collision resistant. Okay? But if we can find a function which is in this little area here, which means it satisfies all three conditions, that would be good. So, how many people have heard of MD5? All right. Anybody who does anything on the net, downloads, gets an MD5 hash of the file downloaded. Right? And so basically that's how you check that nobody has modified the file. Or actually that the file has not had a bit error during transmission. You just check the MD5. MD5 is called Message Digest 5, and it is described in an RFC. Before MD5 was MD4 and MD3 and MD2 and MD1, but MD5 is kind of is something that most of us are used. And for most distributions, for most things, file distributions, people just, there are MD5 checkers, MD5 creators. Basically, you can take a file and create the MD5 hash value of it, and then you can check it out. But what you cannot do is that modify the file and still keep the hash. That's the problem. Okay? If it was easy, then people will just modify the file and send you the same hash, and then you'll be tricked. So that is not possible. But NIST has an algorithm called SHA, Secure Hash Algorithm. First they had SHA-1, which was updated version of SHA. Then they have SHA-2, which is the second generation of SHA. And now they have SHA-3. So basically, these are secure hashes. Okay? SHA-2 is also known as SHA-224, 256, 384, 512. Basically, and this is, as we'll see, different variations in the keys and the block sizes kind of thing, right? And they use 64-bit operations. So, this one uses 512, not the other ones. But basically, so there are many varieties of SHA, these secure hash algorithms. That is what we will talk about. We are not going to talk about MD at all here. Because MD, if you want to learn about it, you can go to the RFC 1321 and read about it. But we are not going to worry about it right now. So, just like for the files, you can do message authentication. Basically, this really means that authentication means two things: integrity and repudiation. Basically, integrity means nobody has modified it, and source repudiation means that the source cannot deny that they sent it. Okay? And obviously, with MD5 is only gives you the first part, integrity, because there is no secret there. But if you use a secret, then we can claim that nobody knows that secret other than you, so you must have sent it. It's like private key, right? So basically, here is the message you want to send. You send the message, even in clear. If you want to encrypt it, that's your business, but really, we are not really promising privacy. The message, the file is in clear. Everybody can read the file. But we are also sending a hash of it. What we do is we take the message, which is the file. We take a secret key if we need it. And then we go to the H, which is the hash function. And then we add that to the message, just like this message and then the hash file and the hash file. We will have two files, one file and a hash file. And then say this is what is received. The receiver can run the same way if it knows the secret, if there was a secret. In some cases, it could be the public key instead of private key. And then they will run the hash and they can verify, yeah, this is correct. No changes have been done. All right. So you can do integrity, which is with MD5. You can do source repudiation with public keys. And of course, you can do encryption with public keys and private keys. Digital signature. Obviously, if you can have source repudiation, you can have digital signature. You can encrypt perhaps with the private key, and then everybody can prove in the code that this private key we don't know, but from the public key we can show that this was done by him. Public storage. Password storage. So when your password is stored, so remember you downloaded that file with the passwords in it. Passwords are not stored in any encrypted form. They are stored in a hash form. So whatever password you select, when you say change password, you change the password, and that password only hash is stored in the computer. So the system manager can see the hash, but they don't know the password. See, this is why it has to be not invertible. Right? Everybody can see the hash, but they cannot find out the real password. Now, the way the password matching is done is that when you log in again second time and you give the password, that hash is matched. The hash of your password that you gave and the hash that is stored, they should match. If the hashes don't match, then they say wrong password, sorry, try again. So the passwords are not stored. Understand that? It's only the hashes to protect you from the system administrator. Right? Today's system administrator could be system hacker tomorrow. So you don't want that to happen. And so basically employees leave and they become angry and so on and so forth. So we don't want any secrets that they can read. Okay? Password storage. Pseudo random number generation, similarly it can be done by hashing an initial value and then hashing the hash, hashing the hash, hashing the hash again. Just like we saw in the encryption thing. You could be just hashing. So hashes have a lot of applications in cryptographic world. And so we now worry about when can we have a collision. So the best thing to learn about collision is by talking about the birthday problem. Birthday problem is, what is the probability that the two people have the same birthday? That means the same date and month, not the year. Same day and month in a room, in a party. Well, if there are two people, then the first person can have 365 days birth, but the second person cannot have that one day which is the first person has, and 364 possibilities. So the total number of possibilities that is actually 365 square, but out of those 360 times 364 would result in a different birthdays for two people. Right? For three people, the total number of possibilities is 365 raised to 3, but only 365 times 364 times 363. These many possibilities will result in different birthdays for all three people. No collision. If you keep doing this, for k people, you will find out that the total number of possibilities is 365 raised to k, but only these many possibilities, 365 times 364 times so on and so forth, that will result in different. So the probability of no collision is this value divided by 365 raised to k, and this is 365 factorial divided by 365 raised to k divided by 365 minus k factorial. Right? Everybody understand this thing results in that number? Right? So now we have a closed form formula for no common day. It turns out that number is not that small. I mean, that no common day is actually very small. Yeah, no common day is very small. The collision is very common. So, if there are two people, the probability that they will have common is 0.01. But if you have 40 people, 90% chance that two people will have the same birthday. In this room, we have 18 people, so we are somewhere around 40% chance. Two people will have the same birthday. Now, I could ask all of you to tell me your birthday, but I'm not going to do that right now. Okay? And you can do that in any other party. 90% chance. Now, the formula can be simplified actually. Is that common birthday, one pair having common birthday, k people are there, and k times k minus 1. So pairs, total pairs are there, right? If there are k people, then there are k times k minus 1 by 2 pairs. You just take 2 out of k. And there are 365 days. So basically, this is the probability of having common birthday, and this is almost like k squared on the top. And so basically the k, if k is more than the square root of 365, then the probability is more than 0.5. Actually, 365, you can see right here somewhere. Square root of 365 would be somewhere there. So in general, if there are n possibilities of any hash table, the square root of n trials will find the collision. So you keep trying different numbers, and the square root of n, where n is the size of the table, trials will get you the collision. So we want the collision resistance, so basically we really want n to be large. So probability of hash collisions, if you have arbitrarily linked message goes to fixed length hash, so many messages will map to the same one. How many messages you have to try? If you have 1,000-bit messages, then total number of messages is 2 raised to 1,000. However, if they hash to 128 bit, then the total number of possible hash values is 2 raised to 128, and therefore 2 raised to 872 messages will hash to the same value. Each value represents 2 raised to 872. That's a lot of messages go to one position. And to find that two messages, all it takes is 2 raised to 128 by 2, which is 64 tries. 2 raised to 64 might be large, but if you have a 64-bit hash, you can break it in a minute. I mean, not a minute. You can break it very easily today. Even probably 2 raised to 64 is probably easy now with all this fast computers. So the hash sizes that you need to be not able to, so that people cannot find a collision, are becoming bigger and bigger. The key summary is that the hash size, if it is n, then n by 2 trials are required. 2 raised to n by 2 trials will be required. Square root of n. All right. So basically, what the way we use in the cryptography is that we take a hash function and we feed a block to it with some secret ID. Then whatever comes out, we use that as the initialization vector for the next block. So it's just like the previous block-based encryption, now we have block-based hashing. Okay? These are all the blocks, y0, y1, yl minus 1 are the blocks. At each stage, we take the output of the previous stage and then combine with the block, hash it, and hash it. At the end, you get a hash, which is real good hash. If any of these bits are changed, all these bits, then this hash will change. So block ciphers can be a hash function. We already saw those blocks, so those blocks could be, block ciphers. So 64-bit is not a good size for hashing. As we said, because 64-bit will require only 32-bit trials, 2 raised to 32 trials, which are easy. And so then they are susceptible to meet in the middle attack. Why they are susceptible to meet in the middle attack? Because somebody can take your file and take your hash and change the file and change the hash and send it out as the correct answer to somebody else. Right? So because you can find the collision. So that's all there is, meet in the middle. Is that somebody can modify it and you will not know it. So let's go to SHA. Secure hash algorithm. And before this was MD5 by Ron Rivest. Now Ron Rivest is a very creative person. Professor at MIT. Remember, Ron Rivest is the R of RSA and R of RC4. Obviously RC4 means there were RC1, 2, 3, 4, 5. MD5, MD1, 2, 3, 4, 5. So he is father of cryptography in that sense. And so he had MD5. And then obviously the NIST ran a competition in '93. And so this is an extension of MD5, and SHA-0, it was not used. They published SHA-0, but it was not used. That was called SHA, but not used. So then they had a modification called SHA-1. Now SHA-1 produces a 160-bit hash. And SHA-2 produces 224, 256, 384, 512, different versions. Now SHA-1 is in common use. It is used in TLS, SSL, PGP, SSH, SMIME, and IPsec. I hope you know all of these words. TLS is transport level security, which is same as SSL. SSL is the old name for the old version of the protocol, SSL. HTTPS. When you use HTTPS, you are using this hash SHA-1 somewhere in that SSL. Right? PGP is a pretty good privacy. That's an email system which gives you good privacy. SSH you have used for telnet kind of stuff. SMIME is secure mail, whatever mail protocol. Basically, mail in. I don't know the right word, but basically when you send a mail, multimedia mail, it is encrypted in, it is basically transmitted as a MIME, and secure MIME is basically a secure version of that, so that it is, nobody can read it. Mail Internet Multimedia Extension. Multimedia extension. So basically, multimedia extension means that you can send a file, you can send a program, you can send a voice, and for that they define MIME. This is secure. And IPsec is IP security. So this is required by law in US government applications. Used in digital signature standard. Pseudocodes for SHA are available. So basically, if you never used to use, you ever need to use SHA or implement SHA, don't implement it, just get a code from somewhere. They are available, open source. And if you write your own, then you have to get a certification from NIST that, yeah, your implementation is correct. Okay? Because you may make a mistake. So SHA-1 basically uses 512-bit blocks and 32-bit operations and produces 160-bit hash. So there is a block size, there is an operation size, and there is a hash size. This is the output, this is the input, and this is how much you handle in each operation. Right? 5 passes. So now basically, SHA-1 uses 5 passes, MD5 uses only 4 passes, MD4 uses only 3 passes. So as you go back in time, they are simpler and simpler, and as you're going forward in time, they are making them more and more complex, right? So 5 passes, and we'll see that 5 passes in a minute, of 16 operations each. So just like we had in DES rounds, and so many things in each round. So here we have 5 rounds. Each round has 16 operations. Maximum master size is 2⁻64 bits. All right, and 512 bits are expanded into 5 times 512 bits. So each 512 bit becomes 5 times that. So basically, nth word is exclusive of n-3rd, n-8, n-14, and n-16. So basically, you take 1, 2, 3, 4 words, and you create the 6th word. Right? And then you continue like that. So what will happen is you start with 512 bits. 512 bits divided by 32 is 16 words, is it? 512 divided by 32 is 16. So you start with 16 words, but when you use this thing to create the 17th, 18th, 19th, 20th, keep creating up to 80th word. 5 times 512 is 80 words, 80 times 32 bits. Okay, I think I will stop right here and explain this picture next time.